Hello and welcome to this clip on entropy and disorder. We'll start by looking at disorder as a factor that tends to increase throughout systems across the universe. Then we'll look at the extent to which disorder in a chemical system can be quantified and called entropy. We'll then look at how to recognize entropy changes in some simple examples, how to calculate entropy change given the appropriate data to start with, and then finally how to use entropy change to calculate free energy and use this free energy to predict the feasibility of a proposed reaction. In order for this to make sense, it's assumed that you're already familiar with enthalpy calculations from the first year of the course. If you need to go back and have a look at things like Hess's law, for example, and delta H calculations, it might be worth going and having a look at them first and then coming to this video after you've re-familiarized yourself. So like I just said, entropy tends to spread in systems throughout the universe. A real-life example might be a gas spreading to fill space over time, diffusion. You might have come across it in your earlier schooling on science. And a good example of this might be if you sprayed a deodorant can in one corner of the room, and then slowly but surely the vapour will diffuse across the room. What's happening is that the gas particles are becoming more disordered, and as they become more disordered they spread out. If you imagine, for example, a lorry carrying a payload of bricks, and for some reason the bricks drop off the back of the lorry, they're not going to land in an ordered fashion, they're more likely to land in a random pile. So it's important to recognise and accept that many chemical and physical systems are driven by the tendency to become more disordered. So if we compare, for example, a solid ionic lattice with a gas, obviously the ionic lattice will be moving slightly, so there'll be some slight vibration going on within the lattice, but it's much more fixed in position and the ions are not moving anywhere independently of each other. If you compare that with a gas on the right hand side, there's random disorder throughout the gas. So therefore a solid ionic lattice is said to be less disordered than a gas, so there's less energy being dispersed around in a solid lattice, so it has a lower amount of entropy. So entropy is essentially the dispersal of energy and disorder within the chemicals that actually make up a chemical system. So if you're looking at, for example, a chemical reaction, you've got the equation. You'll have changes of state and you'll have the mole ratios. If it's going from reactants to products, the products will have more moles of gas. The products might include melting or boiling. If that happens, that means the entropy change is going from lower entropy to higher entropy, so it's a positive entropy change. And as you'd expect, more moles of solid being made, or perhaps freezing or condensing, would mean a more negative entropy change. So what you've got to do is look at the reactants, look at the products, and decide which one has more or less entropy. That will help you decide if there's been a positive entropy change or a negative entropy change. So when we're given standard entropy data for each individual reactant and each individual product, we can work out the entropy change of the overall reaction. So let's do a typical reaction. Now you've come across this equilibrium before, but it's being written as the Ford reaction here. It's the Haber process to produce ammonia. In an exam question you'd be provided with the entropy, the standard entropy for each of the products and reactants which you've got in the table. All you have to do is plug these numbers into the entropy change calculation in the box. So you start by writing out the logic behind what you're about to do, so the examiner can see where you're going. Then you plug the numbers in, lay it out nice and neatly, give the correct units, and underline your answer. So it's quite a simple process this. They'll give you the data, all you have to do is remember that particular equation. So you might want to pause and make a quick flashcard of this particular equation before you go any further, and make sure you memorize it when you practice this after the clip. So once we've got the delta S value, or the change in entropy for a reaction, we can start to work out the free energy. So you'll notice that I've drawn attention to the units, but also in particular in blue, the unit for entropy change. It's been converted to kilojoules per Kelvin per mole because of the kilojoules per mole in each of the other two components, as per the highlights. So make sure if you do a flashcard for this that you also put the conversion of units for entropy. So pause the clip again, grab a flashcard and put this down before the next screen comes up. So before we go any further, why don't you grab a piece of paper and see if you can do these simple questions on entropy theory. So the first one, delta G, will be called the standard free energy. The second one is the temperature at which the reaction occurs. The third is the standard enthalpy change, and the fourth is the standard entropy change. Please make a note of the units. I'll put joules per Kelvin to the -1 per mole to the -1, but I put a footnote underneath saying that it would be converted to kilojoules per Kelvin per mole. And when I say standard, that means 298 K and 100 kilopascals. So looking at the first two examples in part B, in the first instance you've got 2 moles of solid and 1 mole of gas becoming 2 moles of solid, so it's a decrease in entropy. In the second one, you've got 2 moles of solid and 2 moles of aqueous becoming 1 mole of aqueous and 1 mole of gas. That's an increase in entropy. So in the third one, it's no real change in entropy because the 2 moles of gas on each side are unchanged, they're not different from each other. So there's no change in entropy overall. And in the last one, there's a definite increase in entropy because 2 moles of gas on the left become 4 moles of gas on the right, so that's a clear increase in entropy. So before we go any further, a little bit of basic maths. You have to be able to break down this equation into any one of its components and rearrange it so that component is the subject to be able to perform entropy and free energy calculations effectively. So the reason we're interested in being able to rearrange this equation is because we want to be able to calculate the value for delta G and in particular its sign. So if delta G is negative, the reaction is feasible. If delta G equals 0, the temperature, the value of T, is the minimum temperature for the reaction to be feasible. And if delta G is positive, the reaction is not feasible. So feasibility is a balance between delta H, T and delta S. So if we take reactions at room temperature, around the value 298 Kelvin, delta H will be quite a lot bigger than T delta S. So the delta H value is what largely determines the delta G value. But as the temperature rises, obviously T will become bigger, and therefore with it, the T delta S part of the expression will become bigger. So when T delta S equals delta H, then delta G will equal 0. So at this point, T will be the minimum temperature for feasibility. So let's try and summarize this gentle balance between delta H, T and delta S by doing a table. So let's start with the two extremes of feasibility. Feasible at all temperatures means that delta G must always be negative. The only way this can happen is for delta H to be negative and delta S to be positive. If it's the other way round, delta G is always positive, so that it's not feasible at any temperature. So you might want to do a flashcard of this table and use it to help you do some predictions when you come to do some practice of exam questions that ask you to do that. So it gives you an idea of the mathematical balance between the positive and negativity of the different components of the delta G expression. Right, so let's have a look at some worked examples. So here's a typical exam question that gives you some delta H values and some entropy values as well. So the first part is to calculate the standard enthalpy change for the CaO reduction in the equation. So the equation is obviously laid out. So going back to your enthalpy calculations from last year, your first year of chemistry. It did say at the beginning of the clip that you'd need to be familiar with these. You can put them into action here. And obviously we ignore the enthalpy of formation of individual elements that are uncombined. So the carbon and the calcium in elemental form have a formation enthalpy of 0. So let's move the page down a bit, keeping the data to hand. So we start out by writing out the formula or the equation that we need to put into action so the examiner can follow what we're doing. So just bringing the page down so you can see the formula, the equation rather, the balanced equation, we can enter each of the values from the final row of the table of data, because this time we're dealing with entropy. And that gives us positive 193.6. So it's a positive entropy change. And you could guess that obviously because you're forming a mole of gas that you didn't have before, in the form of the carbon monoxide. The next thing they want us to do is to calculate the minimum temperature at which the carbon reduction in the equation is feasible. So let's bring that down, but keeping our data to hand so that we can actually see what we're doing. So the first thing I do is I put in my delta G equals 0 statement and I connect it to the delta G equation. So that means that delta H is equal to T delta S if delta G equals 0. And rearranging the equation the same way that we talked about earlier, it's T is delta H over delta S. So notice that I've converted my units by dividing 193.6, my delta S value, by 1000 to convert it to kilojoules per Kelvin per mole. So that gives me 2711.78 kelvins. It didn't say that the minimum temperature had to be in degrees Celsius, so we don't have to convert back to degrees Celsius. So I can leave it as Kelvin. Let's now have a look at the mark scheme to see what we picked up. So you can see quite clearly that we've got 525 and plus 193.6. We used delta G equals delta H minus T delta S. We said delta G equals 0. So therefore we did the conversion, delta H over delta S equals T. And we got close to 2712. We did 2711.78. So that gives us a total of, including the fact we did the conversion, 7 marks. Happy days. Okay, so hopefully you found this a reasonably useful introduction to entropy and feasibility. If you've got any queries, then do jot them down and bring them into one of us in a subject extension at college, or perhaps go and see your teacher next time you're in. But in the meantime, thanks for your time and see you soon.